The next part of the project is to design our anchored wall. Oops. And again, we're going to consider several different cases. In this situation, we're going to look at 5 different cases, and then we're going to evaluate each one and make an assessment about how deep the wall should go. So our goal here is, how deep does this wall need to go? So the first case, we put the wall down 10 feet into the ground. So this is the ground surface here. Again, it's 30 feet high above the ground. And then we want to know how deep below the ground. So the first one is 10 feet below, then 15 feet below the ground surface, then 20 feet below the ground surface, 30 feet, and 45 feet below the ground surface. So those are the 5 cases. I'm going to do one of them for you to show you how to do it. If you remember, we did our lines, and again, we had 1200 PSF in the active zone at 0. So each one of these cases has 1200 feet at 0. Oops. Now, we called that line 1. And then we had the line going from the 1200. This is the net stresses. So to get the net stress, it looks like this. And when we got it 65 feet below the ground surface, it was 17,600. So each of these cases has the same active and net stresses, basically. So all the same net stresses. It's just that the question really becomes, as we're going to find, is, what is the stress at the base? What is the net stress here at the base of the wall? So that's one of the things we need to find along the way. Now, we wrote an equation. Like I said, we have line 4 here. We have the equation for line 4, and that's going to get us to the stress at the bottom of the wall. So do all 5 wall depths. I'm going to do one of them for you, so you really only have to do 4. And then our goal is to get a factor of safety of approximately 1.5. So our goal is to choose a depth. Here are my depths here. So this is the y-coordinate to the base of the wall, -10, -15, -20, -30, -45. And then we're going to have a different factor of safety for each one of them. And then we want to pick one that's going to be, closest to 1.5 approximately, but the real answer may not be -10, -15. The real answer may be, for instance, -27. Maybe at -27, this is not the answer, but maybe at -27, the answer is factor of safety 1.5. So we're doing all these different cases so that we can make an assessment. We can figure out how the factor of safety varies with depth, and then we can make an approximation as to what depth we should go. All right, let's take a look at the solution template that I'm giving you here, and I'm doing a lot of the work for you. Well, in a way, we've done a lot of the work, so I'm helping you out a little bit, but you've done enough of these that you can do this if you had to. So again, I'm using square as the line number, circle as the area number. And so I have my line, I'm looking at my wall, looks like this, with the net stresses. And we are going to do the case of the wall going to -20. So if you look at this, what you find is that areas 1, 2, and 3 never change. So for each of these cases, for the different wall depths, the base of the wall, there's my different ones, negative 10, negative 15, negative 20, negative 30, negative 45. So I've got my different cases there. But what I find is that if you remember when we came up with these equations for the net stresses, that line 4 here crossed 0 at a depth below the ground of 4.15 feet. So that doesn't change. That doesn't change. So since, in other words, our first one is negative 10, well, at negative 4.15, it crosses 0. So areas 1, 2, and 3 will be the same for all of these different cases. So I'm just going to do areas 1, 2, and 3 for you. You can use them. And the moment that they cause. But I'm going to show you how we got them just to be complete here. So if you remember the equation 1, line number 1, this was our equation for line number 1. And now our anchor is at 5 feet down from the top. So it's at 30, the wall's at 30 feet at the top. The anchor is at 25. So it's 5 feet down from the top. And remember, our coordinate system is set here at the ground surface. So we're taking this as being x, this as being y, and there is my origin right there. So that means that my anchor is at y equals 25. So when I have equation 1, which is the equation for this line here, if I put in y equals 25, I get x equals 200. So in other words, at the anchor depth, this stress is 200. And remember, we ignore the very top stuff. So that we're just cutting that out. We don't need to find that area. We're just taking it as 0, anything above the anchor. So we're just looking at what's going on below the anchor. And we find the stress there is 200, which means that I can get area 1 here simply by taking it's a rectangle, so it's base times height. So the base is 200, the height is 25, so 200 times 25 gives us area 1, and that ends up to be 5,000. The moment arm, remember now we're taking moments about the anchor point, which is up here, and it's a rectangle, so the moment arm is going to be half the height of half the 25, so it's going to be 12.5 feet for that moment arm. For area 2, I know this is 1200, this is 200, so that the base of that is 1200 minus 200, which is 1,000. 1200 minus 200 is 1,000. And again, the height is 25, but it's a triangle, so it's 1/2. So 1/2 the base times the height, BH, 1/2. 1/2 the base times the height for area 2, and that gives me that area 2 is 12,500. The moment arm is going to be 2/3 of the height. So 2/3 of 25 is 16.67 because it's a triangle. And then for 3, I know that the height is 4.15, the base is 1200, so it's going to be 1/2 4.15 times 1200, 2490, and then the moment arm is going to be the 25 plus 1/3 of 4.15 plus 1/3 of 4.15, and that works out to be 26.38. So I have the moment arm for that. I have the areas. So I can get the resistance, the kick out moment for that portion, which is going to be 5,000 times 12.5 plus 12,500 times 16.67 plus 2490 times 26.38. That works out to be 336,600 pound-feet. And like I say, that's going to be the same for all cases. So we can just use that number as the kick out. We need to find the resistance here. So how do we get that resistance? Well, the equation for line 4 is this: y is equal to 0.00346x minus 4.15. And my goal is to figure out what is x. My y, I have taken it as being negative 20. So for this particular case, we're at negative 20. That's my y. Remember my coordinate system again. The origin of the coordinate system is here. So my y is going to be negative 20 to get the base of the wall. Each different depth, you're going to have a different one. So those are other y's, these are other y's to put in there. I solve for x in this equation. So in this particular case, I take the negative 20, I put it here, I solve for x, I get that. Well, I guess I can put the that value of y right there. So I get my value of x is that. So that gives me this, the base, which is 4581. And then this, the height, is going to be what? Well, in this particular case, the height is going to be this distance 20 minus the 4.15. So 20 minus 4.15 is my h for my triangle. My base for my triangle, we've already figured out, is 4581. So 1/2 the base times the height is shown right there. And I get my area 4 is that. And then I need to get the moment arm for area 4, which, again, we're taking moments about this point here. So I need to get what amounts to being this distance, which is going to be this distance, which works out to be 29.15, just 25 plus 4.15, plus 2/3 of my h of my triangle. So 2/3, 0.67, h of the triangle, and I end up with my moment arm of being 39.7. So I take my moment becomes this number of the area times the moment arm. I get that. So this is my resisting moment. To get my factor of safety, then what do? I take the my factor of safety works out to be the resisting, which is 1441, over the kick out, which is 336,600, and that works out to be 4.28. There it is right there. So that's the number I wanted to get out of this. all you need to do, fill out these lines here and get these other factors of safety. And again, your goal is to figure out where does it seem to be closest to 1.5, and then you should interpolate. In other words, if the answer is someplace between -30 and -45, so in other words, then you should interpolate to get the best number. Oops. Okay. That is the description of this part of the project.